Greetings, chemistry students. Today I'm going to introduce you to what can be one of the most confusing concepts in all of chemistry. It's called equilibrium. And if you were to take AP chemistry in the future or college level chemistry, in AP chemistry, I spend a little over 2 months teaching equilibrium concepts. And here I'm going to do it in a day. But the first thing is that a lot of chemical reactions are considered to be reversible, where the reaction can go forwards and then it can also go backwards. Irreversible reactions are ones you're more familiar with, like uh, fires, burning, those are non reversible. Baking a cake, you can't then put it in the refrigerator and have the cake unbake itself. But a lot of chemical reactions are reversible. And if you have the forward reaction and the reverse reaction happening, and they happen at the same rate, the system is said to be at equilibrium. And so that doesn't mean that you have equal amounts of reactants and products. It just means that their concentrations don't change. And all chemical reactions proceed to an equilibrium state that is described by what is called the equilibrium constant, which is represented by the capital letter K. And they use a K because in German the word constant is spelled with a K as opposed to a C. And so for any chemical reaction, such as this hypothetical one where A plus B makes C plus D, and the coefficients in the reactions are little a, b, c, and d, your equilibrium expression says that K equals the concentration of C and times D raised to the powers of their coefficients divided by the concentrations of your reactants raised to the power of their coefficients. Now, these little square brackets, those mean concentration or molarity. And so essentially it's the product concentrations raised to the power of their coefficients divided by the reactant concentrations raised to the power of their coefficients. Now, the larger the value of K, the further the reaction goes to completion, because at equilibrium you'll have a lot more of the things on the numerator than the denominator. So reactions that go very far to completion, they essentially go all the way, would have very, very large values of K. We're talking like in the millions, billions, trillions range. For reactions that don't go very far to completion, that barely happen, they would have very, very small K values, because you would, when the reaction reaches equilibrium, you would have mostly reactants and very few products. So you'd have a lot in the denominator, a little bit in the numerator. Now, K changes with temperature as well. It's just equilibrium is temperature dependent. And the last thing I want to talk about that goes with equilibrium is something called Le Chatelier's principle, which says that if you have a system at equilibrium and you apply some sort of stress to that system, then your reaction is going to either run in the forward or reverse reaction to minimize that stress or to try and undo what you did. So if you increase the pressure, the reaction is going to go in the direction that produces less gas molecules to try to bring the pressure back down. If you heat a reaction up, it's going to shift in whichever direction will remove that heat to cool itself back down. Or if you add some reactants, it's going to run towards the product side to remove them. Or if you added products, it would run backwards. So essentially, Le Chatelier's principle says that chemical reactions at equilibrium will try to stay at equilibrium, and if you change things, the reaction will run in whichever way undoes what you just did. And so we're going to look at a couple of examples here. So this chemical reaction right here is one of the most important reactions ever developed. It is called the Haber process, named after the evil genius Fritz Haber, who developed the way to turn nitrogen gas and hydrogen gas into ammonia. Now, this reaction is also a reversible reaction, so let me draw the double arrow there. And I wrote over here, delta H is negative, meaning this reaction is exothermic. It releases heat, so I'll just write heat over here as a product. Now, the reason this reaction is important is because ammonia, NH3, is used as a nitrogen-based fertilizer. And you need that in order to help grow crops and have very productive agriculture. You need nitrogen. It's typically the limiting nutrient for plants. And so the Haber process allows us to take nitrogen from the air plus hydrogen gas and combine it to make ammonia that can then be used to synthesize the fertilizer. Now, this reaction has a very small K value. In other words, this reaction favors the reactants. It does not go very far to completion. If we were going to write an equilibrium expression for this reaction, you would say that K equals the concentration of NH3, which is our product, squared divided by the concentration of N2. Now it just has a coefficient that's understood to be a 1. So we don't write an exponent there. You don't write a 1 when you raise something to the first power. Then times the concentration of hydrogen cubed. So that's our equilibrium expression. Now, if we were trying to force this reaction to go towards the product side so that you can actually make ammonia, one thing you can do, since this reaction generates heat, you can cool it. So you can cool it down. Another thing, since this reaction has 1 plus 3 or 4 gas molecules on the left side, 2 gas molecules on the right side, the other thing you can do is increase the pressure. And the third thing you can do is remove the NH3 as it forms. So essentially, Haber developed a way to take the NH3, the ammonia, and remove it from the reaction as soon as it's formed, which is then going to cause the reaction's equilibrium to keep shifting towards the product side to make more of it and more of it and more of it as you keep removing it. It's essentially never going to be able to reach equilibrium. Now, the other thing you have to do is, if you think back to what we looked at last week, if you cool a reaction down, then the reaction is going to happen more slowly because you're going to have less effective collisions. So the other thing that Haber did is he added a catalyst, which does not change where your equilibrium ends up, but it makes the reaction happen fast enough that you can actually make money by doing this. Because ultimately, the goal of chemistry is not just to understand things, but to have chemical engineers be able to use our knowledge of chemistry to make money and make life better for all of us. So that's your little lesson on chemical equilibrium.